last video, I left off with connecting my 287 math coprocessor down here into my system. And that included a bunch of control wires, which I was using yellow wiring for most of my control lines, a clock line, maybe some values some signals I was pulling up, or pins I was pulling up or down, a couple of address lines that took me over to A1 and A2 so that I could treat this as an I/O mapped device and write configuration information to it, read from it, etc. And then I have all these data lines that I pulled right off of the processor up here. Well, in this video, I'm going to pick up with where I left off there and get into actually trying to get something to work on the math coprocessor, to see if it even works, because I'm assuming my design off of just reading the data sheets and reading these other books and such is going to work, but that doesn't mean it is actually going to be the case. I am using this book as a reference. This book here is the 80x86 IBM PC and Compatible Computers, volumes 1 and 2. And I've mentioned this book in previous videos, but this book has been a really handy book. I think it's a great book. It's got a ton of content, a lot of different topics, and I would highly recommend you grab a copy of this if you're getting into this 8086 or 286 type of hobby builds or whatever it might be. In that book, there is a section on the math coprocessor. One of the tables they put in the book is actually a reprint from Intel, but it just shows you the difference in performance from like an 8086 over here to an 8087. So this is execution time, and just look at that difference. That's gigantic. So as I'm getting into writing some assembly code, I'm probably going to leverage this coprocessor more than I would have thought I was going to do. Even for things as simple as adds and multiplication, this is going to come in pretty handy, I think. So I'm going to try to take advantage of that where I can, and try to learn my way through it as I move forward. One of the things I also need to learn is a bit about floating point numbers and how can I represent those and work with those inside of my assembly code. And it's interesting as I go through this, and I'm not going to try to get into the mathematics or the background of any of this, but in the book they talk about how would you convert, for example, a real number into something that we can work with inside of assembly. And here they convert 9.75 to basically a single precision floating point. And this is something that we want to be able to represent in binary or hex, essentially, is that number. And you can jump to the very bottom and it shows that 9.75 ultimately is going to be represented as 411C0000. And they show you the steps above in this example, and you can read what's on the background of this over here down to the left of how they're coming to that. So for example, step 1, convert 9.75 to binary. So what that means is, what's 9 in binary? So there's my 9. 0.75 is 1 here, and I understand the way you would typically do that is you take this 0.75, you'd multiply it by 2. That would give you 1.5. You'd put the 1 here, and then with the 0.5 that you now have, you would multiply that by 2. That would give you your other 1. So Google that, and some of you probably know how to do that very easily, but that's new for me, so I'm probably not explaining it very well. But there's a process to go through to convert this decimal into a binary number. From there, look at it in scientific form. So shift the decimals, put the exponent 3 over here. Is it signed? Is it a positive? Is it a negative? So put a 0 or a 1 for this first bit. The next set of bits are basically, I can come down here and look at this example. So here they're showing 1.xey, and it says bit 31 is positive, 1 for negative. And then the exponent portion, y, is added to this constant 7f to get what they call a biased exponent. And that's placed in bits 23 down, or 30 down to 23. And then the significand, if that's pronounced correctly, XXXX in this format, that's placed in bits 22 down to 0. And so in their example 9.75, they go through those steps and they get this type of thing. If you were going to test me on that, I would fail the test. I'm not going to remember that off the top of my head, but I'll come back to this reference, and maybe after some time it'll get easier to kind of remember those steps. And I imagine I'll probably end up writing some routines that do a lot of this type of stuff in my code. So that's something to consider, and I'm actually in some sample code I'm going to show you coming up. I'm doing a little bit of that just so I can print some of this stuff out to my screen to see if things are even working, to kind of test the system out a little bit. Other things to maybe pay attention to, there are registers that I can now use, and it says in the 8087, and I'm assuming this is the same in the 287, but 8 general purpose registers, and they are 80 bits wide, so those are really big registers, and that's pretty cool. So I've got 8 80-bit registers that can get used here, and they refer to them as ST0, ST1, ST2, etc. Number 1 down below, all the mnemonics that I'm going to use that are taking advantage of the coprocessor. We'll start with the letter F, and I've got to initialize the coprocessor. Number 3, when a register is not identified, ST will just simply be assumed to be ST0. And then they say ST0 is the top of the stack, ST1 is the next one down, ST2 is the next one down, etc. And then you've got some data types over to the right. So I now have a DD, which is a defined double word. Use that for a short reel. DQ, DD, I'm going to use for short integer, DQ for long integer, DT for packed decimal, and DT for temporary real. I can't say I really have worked with any of those, so that's all going to be stuff for me to play around with and learn a bit as I move forward. In the code I'm going to show you in a little bit, I am using DD, so you'll get to see that, I guess, in action a little bit. And here are some of those instructions that, well, I think this is all the instructions that aren't configuration instructions and such for that coprocessor. But you can just look, and there's some really interesting things here as I look through this. So, take a look at that. But like for example, FLDPI, that loads pi, the value of pi, which it's that easy. Okay, load up pi. Or I can go down to FMUL. I want to multiply. So it's to multiply numbers. It's that easy. I can just use this FMUL. A lot of other stuff here on the screen, and I by no means know much about any of these. I'm going to just start chipping away at them and start learning them little by little, whether it's addition, subtraction, multiplication. Those will probably be the simple things that I start with. And this is an example that they gave in the book, and I thought this might be a good one for me to implement and just see if I can make this work. And so what this example is doing is calculating the area of a circle. And they're going to use, you can see over here, a radius of 91.67, and they're going to put that into R using DD and then 9167. And then they're going to basically calculate what is the area of that circle and store it, and they're going to go ahead and store it down into this thing called area, which they put up here, area DD question mark. So that's the code that this isn't quite how I'm going to do it in my setup using NASM, but that's what they were using, and that was a nice guide for me to try to build off of that and re-implement that in my code. Over to the right are numbers, that conversion I was talking about before. So this first number, the radius, 91.67, is going to look like this, 42B75708. And they kind of go through, that's 91.67 and all the way out here, but kind of show how that breaks down as they go through this. So take that into binary and eventually fill all of this out to get to this hex that you see up top. Now that's an input, so I'm going to feed that in, but then the question is, what should I get out of this if it actually worked? So when I get done with this and I want to go look at this area, what I'm hoping to get out is 46CE400C. And if I can get that back out, then that means I was successful as far as calling the appropriate, functions or instructions on that math coprocessor. So that's going to be an indicator of success. And so sending that in, trying to get that out. So I did send in 42B757-0A, and if I back up, that matches what I should be sending in. So that part of it, okay, I got 91.67, loaded up, and I read it back out and printed it to the screen, and that's the first part here. And then I ran through the steps, and I went and read back area, and I got all Fs. And that obviously isn't what I was hoping to see. I was hoping to see 46CE400C. So I knew I had a problem at that point. In the last video, I mentioned an area that potentially would be a problem, and I wasn't sure if it would matter or not, and it ends up that it does matter in my build. This is what I had on my schematic for my math coprocessor, and this is what I ultimately changed it to. And the only difference is, instead of grabbing the data off the processor, I am grabbing the data from the bus, meaning that I'm grabbing it on the other side of the transceivers. What was happening, I think, is when I was trying to read the data from I'm going to call it the inside of the transceiver, closer to the processor, at the same time, the transceivers were trying to bring in values from the bus, and it seemed like the math coprocessor was not winning. Whatever signal was coming in from those transceivers was ultimately taking the values that the processor was reading. I'm sure there's explanations for that. Some of you can probably explain that pretty quickly, but I'm just going to say that my guess is that 287 just was not powerful enough to basically overcome those transceivers. Now, I would say on my bus, I do have my bus pulled up. So I have pull-ups on all of my bus lines. So I did go in and take out those pull-ups, and then of course that dropped everything to 0, but then I was reading all 0s instead of all 1s when it came to reading back from the math coprocessor. So that still wasn't good. So I thought, okay, let's instead of grabbing the data right off the processor, let's grab it from the bus, and that was a good thing. That ended up taking care of it. Now let me just show you something else I was doing for troubleshooting along the way. I used my debugger to capture some logged output, and this is actually, I'm finding this to be really handy. And so I've got a previous video where I use this Arduino and I capture the data in a Windows app, and now I can write it out to a CSV or a text file, so I can let it run and run and run and just capture things. But I did a quick capture when things weren't working, and I've got columns over here that show me when certain things are enabled, so I can look for at what point was I using my, well, there you can see PPI 1, there's going to be PPI 2 in here. There's also going to be now a math that you'll see get activated. So this is where I'm actually seeing activity to the math coprocessor. So I can see, yep, it's accessing it at F8. That was part of my address decoding for the coprocessor. I covered that in a previous video. And then I can look at this, and I'm looking for a 0 in the I/O, and an IOWC 0 means it was writing. So at this point, it was writing this value 06D9 to the math coprocessor. Then it wrote a 45 to the math coprocessor. It wrote a whatever 570A to the math coprocessor. And let's see, are any of these reads? So this one's a write. This is all writing to the math coprocessor in the code that I'm about to show you. But at some point I got further down, and where I'm supposed to be reading back from the math coprocessor would be down here. And so now instead of the write being the 1, it's the read being the 0. The read is the 0. So this tells me I'm reading from the math coprocessor. I'm reading from address FA. That's an IO address, not a memory address. And it was coming back with all 1s. There's my all 1s that I was pulling back. So I knew something was wrong at that point. And I had done some testing in my code just to write out some values that I could go look at. And I wrote out the values 1, 2, 3, 4, 4, 5, 6, 7. and then basically put those into this spot that's supposed to hold the area. And then I actually go to the math coprocessor and say fill in area with the result, and I was getting all ones. So I took out the call to the math coprocessor and I got out my 1, 2, 3, 4, 4, 5, 6, 7. So that told me I was getting to my memory spot okay. There's something though wrong with my ability to read back values from the math coprocessor. But I found this interesting, and it lets me also kind of see what is happening behind the scenes. How is my processor talking to the coprocessor? I'm not calling these specific lines specifically. A lot of this is happening automatically based on things that I'm doing in assembly with just simply some of those those different F mnemonics. Let me go over to the code at this point and just talk you through what I have so far. And so this is my current 286 code that I've been working on. And if I get into this a little bit here, I'm going to kind of scroll down. This is building off of previous videos, so I'm not going to get into actually getting to the interrupt routine or talking about the PPIs or anything like that. But what I do have, a real quick note, is I have an interrupt routine. So if I press a key on the keyboard, I can go ahead and run something. And in this, what I'm going to do is if you press the escape key on the keyboard, then I'm going to jump to a procedure. First of all, I'm going to clear the LCD. So I'll clear whatever's on the screen. And then I'm going to go to a procedure called test math co. And so then if I scroll down, I've got a test math co in here somewhere. I think maybe it's above. So here's my test math co. And basically here I've re-implemented what was coming from that book for the example of calculating the area of that circle. So I have R, I say DD, and I want to put in the value 91.67, which translates to that number, 4257570A. And in the ROM, this is how it's stored. So that's part of the gymnastics I had to do too, is as I was looking at what I was assembling and looking at how things are stored, this is how it's stored to the right. This is the actual, if I pull it back, little Indian, and it's basically 4 bytes, that represents 91.67. So I get that into R because I'm going to use that as my radius. I then call a procedure to ROM. I mentioned that previous. All that's going to do is change my data segment to be up in my ROM area. So change my data segment to 8000, and then go out to R and go forward 3 and read that value into AX and then print it. And previously I mentioned I had that print char hex routine I wrote. So the goal then is if this works, it's going to jump up into ROM. It's going to jump over here to the end and grab this 42. So basically it's going to go forward 3 bytes and grab the 42 and print it out. Then it's going to go forward 2 bytes, grab the B7, 1 byte from R, get the 57, and then get R, which it's going to pull back a 0A. And that's because on the screen I want it to say 42B757 0A. This is kind of more the, not the little Indian format that is being used to store it in ROM. Then I use some of those F mnemonics here. So these instructions, I initialize the math coprocessor. I load R as a D word. I then multiply R times R. So when I loaded this, it went into that first register of the coprocessor and I multiplied it by itself. I then have a simple instruction to load pi. Well, that's easy. So I load up pi. And when I load that, it's going to go into the next register down, which is this ST1. So now I'm going to multiply my ST0, which is my R squared, if I'm understanding this right, times my pi. And now I've got a result. So I want to do something with that result. So at that point, I jump back. I change my data segment back to RAM 0. So I was up in this 8000 data segment. Now I jump back to the 0 data segment. And for testing, I then moved into this area, a 1, 2, 3, 4, and a 4, 5, 6, 7. And that's what you saw earlier in that Excel file that was showing the logged output, was where I was doing this move. Because again, I'm pretty new to the assembly. I just wanted to make sure I could even get to the right spot in memory, write something and read it back. And this was just a quick test. Put that in there. And then if I skipped this and went straight to some of this down here, I could print back out and see if I was getting my 1, 2, 3, 4, 4, 5, 6, 7. But once I knew that was working, I comment those out. And then I stored the calculated area. So store basically what I've got calculated in memory here on the math coprocessor, get that into area. And that's where basically I was running into challenges that I was seeing, all ones or all hex F here, and I wasn't actually getting what I was hoping to be getting out of it. But I worked through that. I changed again my data lines to come from inside the transceiver to outside the transceiver, and then all of this has been working. So then I call a procedure that says jump to line 2 of the LCD. So line 1 is going to have the value of my radius, and then now I'm going to go to line 2, and in line 2 I'm going to take and write out whatever is basically in this 4th byte of area, 3rd byte, 2nd byte, and 1st byte, and write that out to the screen. And if it works, I should be writing out 46CE400C, and that back in decimal would be this number here. So if I started with 9167, I should be getting an answer of 26,400 and some change. And so if I read this out, that's what I want to be able to see on my screen. And so if I turn on my system at this point, I just come up to a cursor, and the reason I put it in the keyboard interrupt service routine is so that at this point I could flip off of my CAN oscillator to a much slower clock, hit a key, and watch what it's doing at whatever speed I want to run at. I don't want to run a slow clock all the way up to this initialized point, because there's just a lot that has to happen before I even get there. So I put it into the keyboard interrupt. I could get to this point. I could flip to my 5:55 clock. I could turn on my debugger and start recording, and then I could press a key and capture things quite effectively. I'm not going to do that at this point. It's running a 5 megahertz effective clock to the processor, in the processor, 10 megahertz to the processor. I have it default to come up to the this greater than symbol. I can type in, and that works. And remember, my escape key is what I tied to. So when I press escape, I fed in the radius, and hopefully this is coming through, the light's okay. But at the top of the screen here, I've got 42B7570A, so that's what I fed in. And what I got out of it is 46CE40AC. And if I compare to what I was hoping to get, that matches. And so that tells me that this is working. So I have given a number for my radius. I've shown it to the screen just to make sure I can read it back, and that what I have in my ROM is correct and being read back correctly. I initialize my math coprocessor. I go through the actual calculations. I store the result into area, and then I show that out to the LCD in this same type of format. So I think I'm sitting in a good position at this point. This build is getting there, I guess. So if I go back to my initial maybe a design I was doing, just kind of trying to sketch some of this out in a wireframe on the computer, the main pieces I was hoping to have in here are getting there. So I think I'm sitting pretty good. So I am going to call this a win. I'm happy with where I'm at. Math coprocessor is working. Really, if I go through all the pieces here, we've got, kind of backing up from the beginning, we've got the clock and the bus controller here working, processor with the hat. I've got my latches and transceivers getting everything out to the bus. We've got my interrupt controller, my PPIs, the keyboard, the LCD output, ROM, RAM, math coprocessor. All of that is going pretty well. I do have a PCB coming in, and that PCB really is what you see here. I think I've got most of this in that PCB. So I had also added some ISA slots, not full ISA support, no DMA or anything like that, but should have the ability now to at least experiment with an ISA slot minus the DMA support. And I think the only thing that I know for sure is going to be a problem is those lines that go for data to the math coprocessor, because they're going to have pulled off of the processor and not after the latches. So I will have to do some bodge work there and cut those 16 lines and run 16 bodge wires. So I'm sure that will be a good time. But hopefully I can get that done and then get this system on a PCB version and see if I can make that work. And if I can make that work, then I can figure out what I can do to then expand it and make it better. What's the next step? I think the biggest time investment I have ahead of me now at this point is just simply assembly. I've got the basic hardware, I would say, stitched together. So now I need to actually figure out how to use it all from assembly, and that is my next really big step here, is just to start working on the assembly side of things. If you've got any questions on what I've done so far, do let me know. But this is where I'm going to stop this video. And I think future videos, I'm going to probably get in and experiment with some assembly, doing different things. Also, of course, experiment with a PCB when I get that in-house. If there are other things you would like to see or are interested in, drop me a note and let me know. Thanks.